Good afternoon. This is November the 1st, and this is Calculus 1. And today we're going to talk about solving optimization problems. Before we get started on that, a couple of notes. Exam 2, the deadline for Exam 2 was yesterday. Grades and exams themselves will be available the middle of next week. So if you don't hear from me middle of next week, you might email me next Tuesday or Wednesday to see what the status of exams are. The W day for the semester, the last day that you can withdraw from a class and get a W, is November the 10th. That's the end of next week. So if you have any questions about your status in class, you should always talk to me before you do anything like drop. See where you stand in the class. Talk to me first before you go ahead and fill out the paperwork for withdrawal. Homework 3 grades will be available either tomorrow or Friday. So I'll be posting those in the next day or two. Homework 4 and 5 due dates. Wanted to point out that and remind you that those had been delayed a little bit, that I've postponed the homework 4 due date until November the 8th and the homework 5 due date until November the 22nd. I did email everybody once again a couple of days ago the homework to make sure to kind of remind you of what the homework assignments were for 4, 5, and 6. So we've completed homeworks 1, 2, and 3, and we're currently working on 4, and we still have 5 and 6 for the rest of the semester. And remember, I will drop the lowest of the homework grades and then average the last 5 or the highest 5 as your homework average for the semester. All right, so today what we want to do is we want to talk about solving optimization problems. And so first thing is, what is an optimization problem? And then once we kind of talk about that, then we will be ready to actually solve them, and we're going to write out a method for doing that. So first of all, what is an optimization problem? And the answer would be a problem where you are trying to find the minimum or maximum value of a quantity given certain conditions . All right, the maximum or minimum value is sometimes called the optimal solution. And that's why we get the name optimization problems. But this is sometimes called the optimal solution, the one that's the best solution. And certainly not all problems with the optimal solution be a maximum or a minimum. It depends on the kind of problem you're talking about. But the kinds of problems we're going to center on are ones where the optimal solution for a particular problem is a maximum value for a quantity or a minimum value for a quantity. All right. So what I'm going to do is I'm going to run through the steps for solving an optimization problem. So how do you solve these types of problems? And so I'm going to identify, we're going to actually number the steps at, and I'm going to use this numbering system as I go through and talk about solving different kinds of optimization problems. So the first thing to do is to identify what you are trying to maximize or minimize. All right, so read through the problem and identify that quantity. And so what we're going to do for the sake of these directions, we're going to call this quantity Q. So we're going to call this quantity Q, or P rather. Call this quantity P. All right. Second step, we're going to find an equation or write an equation. Find an equation that gives you P. And you can have more than one variable in that kind of an equation. So this equation may have more than one variable. Okay, so we're talking about that you've got P equals something with more than one variable. So P equals some quantity, something with one or more variables. It's possible you may start out with P being equal just to something with one variable in it, but it's also possible that it may have a function of several variables. So P, might be a function of X and Y, depending on what X and Y are. Or P might be a function of R and H, where R is radius and H is height for some object, etc. Where P is equal to something that has one or more variables. Okay. Step 3. The problem is when you've got a function of more than one variable, we know how to use calculus for functions of one variable. And so if you've got functions of several variables, then you're going to have a problem with as far as the calculus that we know right now. Now, a Calculus 3 student who has dealt with functions of several variables may have an easier time with that kind of problem. But with a Cal 1, with what we know in Cal 1, we have to have a function of one variable also. So we use the conditions of the problem to write P in terms of one variable only. So in other words, P is just equal to some function of X, for example. Now, this process usually kind of runs like this. If we've got that P is some function of X and Y, then there's some secondary equation. And you'll see this referred to as a secondary equation. You'll see this also referred to as a constraint equation because it puts an additional constraint on the problem. And so there will be a constraint or secondary equation that connects X and Y to each other. And so that secondary equation that relates X and Y to each other can be used to take a function of X and Y and rewrite it just as a function of X. Right? So you're trying to connect X and Y to each other somehow so that you can go from a function of two variables to a function just of one variable. All right, step 4. You're going to find and write any restrictions on X. All right, and write them down when you find those restrictions on X. Now, if the problem is an open interval problem, in other words, the restrictions on X give you an open interval on X, then what's going on here is that, so let's say that the open interval, well, we could identify something like A to B like this, then this is going to be a relative max-min problem. But if the problem is a closed interval problem, and there will be some problems we'll identify that are closed interval problems, then this is an absolute max-min problem. In other words, the difference here is that the solution may be at an endpoint. Remember, we've talked about that a few weeks ago, that in a closed interval, a continuous function had to have an absolute maximum and an absolute minimum value. So if we identify the restrictions on our variable x in this problem, and we see that it's a closed interval, it's possible that the optimal solution for the problem may be at one of the endpoints of the interval that you've identified. All right, then the next step. So we've got a couple of steps left to go, and then we're going to walk through numerous problems here so that you can see different kinds of problems and how they're worked. All right, so the next step, 5, we've got this function now of one variable, p equals f of x. We have restrictions on x. We know what the domain of the function is. We know what the effective domain of the function is. The effective domain is just the x values where, for the particular problem you're talking about. If it's a physical problem, there may be more restrictions on x than just if you were looking at it as a purely algebraic function. Okay? So you've got this function p equals f of x. You've got all the restrictions. Then you find, so now you find p prime and find all critical numbers that are in the domain of the function. Find all critical numbers in the effective domain of the function. All right, we typically just one of these. All right. 6. So what we want to do is we want to actually see if that critical number actually yields a maximum or a minimum. So in step 6, we use numerous different ways to do this. Use the first derivative test, to show that the critical number yields a maximum or a minimum. Use the first derivative test to prove the critical number yields a max or a min. Now remember what the first derivative test says. The first derivative test says that if the derivative of a function goes from negative to positive, that means that the function goes from decreasing to increasing, and it means you have a relative min. And then let's say that that's at a, so a relative min would occur at x equals a. And if f prime at a goes from positive to negative, that means the function is going from rising to falling. It means you have a relative max at x equals a. All right, so that's the first derivative test. Or use the second derivative test to prove same things, right? And so in this case, remember, if you've got f prime of a is equal to 0, so if you've got a critical number that yields 0 for the derivative, if the second derivative evaluated at a is positive, it means the function is concave up. It means, so you have a shape kind of like this right here. It means you have a relative min at x equals a. If the second derivative, on the other hand, at a is negative, it means the function at a is concave down. It means you have a relative maximum at x equals a. Right, so this is a different way of doing that, proving that a function actually has a relative max or min at the critical number you found. You could still just look at the graph, or look at the graph of p equals f of x and show that x equals a has got a max or a min at x equals a. So look at the graph of p equals f of x to show x equals a yields a max or a min. And then finally, step 7, last step. So 6 actually proves, is the step where we prove that you've got a maximum or a minimum at a particular critical number. And 7 would be to actually answer the question, which sounds kind of goofy to say, but just because you found where the maximum or minimum occurs doesn't mean you're answering the specific question in the problem. So then you go to the problem, make sure that you're actually answering what they've asked you to find. All right? Okay, so that's our little method for finding optimal solutions for a problem. And so now we're going to go ahead and actually look at some examples of how to do this. Okay, so that's our next step, to actually look at how we can find some examples. All right, so let's look at some examples here. So let's say that we have examples, first of all, for optimization problems. And I'm begging you to go through these solutions that I'm presenting in this lecture and walk through them and make sure that you can actually work through these kinds of problems, or that you understand how I'm working them. Okay? So first problem, let's say that we have a river that's running like this, and not a typical river because the sides are going to be parallel like that. And we want to fence, so we're building fencing here along the side of the river. So this is fencing right here, and we're going to fence a rectangular area alongside this river, all right, like this. And then within that rectangular area, we want to fence again to subdivide the big rectangle into 2 smaller rectangles. So if you look at the river here and look at the red lines that I'm sketching here, the red lines are the fencing. The river is the black line. So notice I'm not fencing along the river right here. I'm just fencing a rectangular area that's right next to the river like that. All right, so there's our start here. And you have, let's say that you have 1,000 feet of fencing. All right, we have 1,000 feet of fencing. So the question is, so here's our question. What dimensions can I fence to enclose a maximum area? All right, that's my question. What dimensions can I fence to enclose a maximum area? All right, so what we're going to do is we're going to actually walk through the steps that I outlined on the previous 2 pages for how to set up a problem like this, or how to actually solve a problem like this. So step 1 is to identify the quantity that you're trying to maximize or minimize. So in this particular problem, the quantity that you're trying to maximize is the area. So we're trying to maximize area. So I'm going to write that down. Maximize area of the rectangular area, of the rectangle. All right, and we're going to call this capital A. We'll call it something. All right, and so in my picture up here, if I go ahead and label this side of the region that or the area that I'm enclosing in this fence, if I label that side X, well then that X has got to represent, because this is a rectangle, it's got to represent this area also, or not that area, that length, and this length also. Right? It's got to represent all 3 of those. So we'll call that side, those sides the length X, and then this side right here, we'll call this side length Y. Right here. All right, so if that's true, then going on to the second step, which is to write an equation that gives us X and gives area as a function of 1 or more variables, we can see just from this picture, you have a rectangle, area is X times Y. right? So there's our equation for area. The problem is it's a function of two variables, right? It's a function of two variables. So we need a secondary equation that relates x and y. Okay, so if you look at the picture, the x's and y's describe the total length of the fence, but I know that the length of the fence is 1,000 feet. So notice that if you're looking at the length of the fence, then you just add the lengths together, x plus x plus x plus y, that's got to be equal to 1,000. And hey, you've got an equation that relates x and y to each other. You get that 3x plus y is equal to 1,000. Right? And so that's our secondary equation. Or sometimes you'll see that referred to as the constraint equation. So that's the secondary equation. All right, so what I will do is I will solve that equation for y. In this case, that's probably the easiest thing to do. So y is equal to negative 3x plus 1,000. And then what I do is I substitute that into my equation. I have a equals x times y, but that would mean that a is equal to x times negative 3x plus 1,000. And boom, what have I done? I've taken a and changed it from a function of two variables. A was a function of two variables. I used my secondary equation to rewrite a as a function of one variable only, right, just of x. How did I do that? I used my secondary equation that relates x and y to each other. And so this is what we're after. This is our function, and we have negative 3x squared plus 1,000. All right, so now the restrictions. Now, from an algebraic standpoint, the restrictions on that equation on x are that there are no restrictions on x, right? That's a polynomial function. That's certainly defined for any x value. But the effective domain is different because the effective domain describes what x values we can use in a practical sense in this problem. And if you look at the picture, right, x represents the width of that rectangle. So x has to be greater than 0, certainly. So the effective domain here is that x has to be positive. There's no question about that. And there's really an upper restriction on x also, because what do we know is that if we know that the fence total length of the fencing has to be 1,000 feet. So we know that 3x plus y has got to be equal to 1,000. And so, if you let y be 0 in that equation, you have 3x plus y equals 1,000. If you let y equal 0, then you get that 3x is equal to 1,000, or x is 1,000 thirds. So what would have to be true? We know that y can't be 0. Y has got to be bigger than 0. So that means x has to be less than 1,000 thirds. So x must be less than 1,000 thirds in our particular problem. So we do get an open interval for this problem that x has got to be between 0 and 1,000 thirds. Right? That's our effective domain, that we can only use x's in that interval. Now, from a practical standpoint, x actually has to be greater than more than just greater than 0. I mean, because if you're saying that it's a foot, if x was just 1 foot, that you have this incredibly narrow rectangle along the river, well, that doesn't make any sense. But from a purely theoretical standpoint, x just has to be greater than 0. All right, so there's our restrictions. And so now what we're ready to do, and let's see, remember, we're numbering these as we go along. So we've got the restrictions. And so number 5 is we're going to find our derivative for this function. And we're going to go ahead and find the critical numbers for this derivative. So we know that a is equal to negative 3x squared plus 1,000. 1000x. And so a prime would be equal to negative 6x plus 1000. And we have that a prime is equal to 0. We're looking for critical numbers here. When negative 6x plus 1000 is equal to 0, which would give us that x is equal to 1000 over 6, or 500 over 3. Or if you want to write it as a mixed number, it'd be a 166 2/3 feet. Right. So what we are saying in this problem is that we believe that that there is a optimal solution, probably at 166 2/3 feet. That's for the x value. And so to actually prove that, that's step 6. Step 6 is to verify this critical number yields a maximum area. All right, so if you did this with the first derivative test, so there's 3 ways that we talked about as we were going through the steps for solving these kinds of problems that we talked about for verifying that the critical number actually yields a maximum. One is to use the first derivative test. So the first derivative test, here we have a prime. Here we have 500 over 3. And we want to see what the sign of the derivative is around our critical number. Right? So we might pick, we could pick test values, just like we did back in the previous couple of sections. We could pick a test value that's less than 500 thirds and a test value that's greater than 500 thirds. So a test value maybe like 100. Remember, the critical number is at 166 2/3. So 100 less than and 200 greater than. So if you substitute 100 into our derivative, which is negative 6x plus 1000, you get a positive value. You get a positive number here. And it means the function's increasing. And when you substitute 200 in there, you get negative 1200 plus 1000. You get a negative value for the derivative. Remember here, you're evaluating a prime at 100, and you're evaluating a prime at 200. And so when you substitute those values into our derivative, you get those signs, and you get that the function goes from rising to falling. And so what do we have here? That this proves that a reaches a maximum. In other words, the area reaches a maximum at x equals 166 2/3, or 500 thirds feet. All right. Now the second way to prove that 500 thirds yields a maximum is the second derivative test. So we use the first derivative test. This is the second derivative test. And I should have put the word test right here. Put that in there. Okay, so the second derivative test involves finding the second derivative for this function. And this actually works out quite nicely here because the second derivative is negative 6. It's a constant. And we evaluate the second derivative at the place where the first derivative was 0, so at 500 thirds. Well, the second derivative is a constant, so it's always negative 6. So the second derivative evaluated at 500 thirds is certainly negative because it's equal to negative 6. It's always negative 6 because it's a constant function. So since the second derivative was negative, remember that means that the function's concave down at the critical number, and this proves, right, that A reaches a max at x equals 500 thirds. Now, I am definitely not telling you that you need to go through and verify that the critical number yields a maximum all these different ways. But what I did want to do is illustrate simply all of these ways so that you can see all of them worked out So you could see how you would use these different techniques for actually proving you have a maximum or a minimum. Okay, now the third way is to actually look at the graph. So we want to look at the graph of a equals negative 3x squared plus 1000x, or y equals negative 3x squared plus 1000x, right, if you're going to graph it, for example, on a graphing calculator, and show that 166 2/3 actually does yield a maximum value, or 500 thirds. So we would actually go to our function here. Whoops, wrong app. And let's see, I'll get it here eventually. Here we go. And we're going to go ahead and clear out this old function here from another class. And we've got the function negative 3x squared plus 1000x. You're not graphing the derivative here. You're graphing the original function plus 1000x, because that's the one we're trying to maximize or minimize. And we want to save that and go ahead and graph this. And we see here, and so what I want to do here is definitely kind of make this a little bit bigger here. I'm going to go ahead and take a picture of this and post it or paste it back into our problem. And this is the function that we're getting here. Let me probably make this a little bit smaller here. Go ahead and paste it in here so I can write on it. And so notice that our function does yield a maximum right about in here. And that maximum, where is that at? That's at 166 2/3, right? It certainly fits our picture right there. And so that, remember, this horizontal axis is the x-axis. A is equal to negative 3x squared plus 1000x. Don't forget that then that the y value is actually the a-axis right here. That's the area axis. And don't forget what x represented. X, you had this river, and we decided we were going to enclose a rectangle like that, along a rectangular area alongside the river, and x represented the width of this rectangle right here. Okay, so 166 2/3 does seem to fit the picture really nicely. And then notice also that this picture does yield the maximum area, what the actual maximum area is. That 166 2/3 is the width of the rectangle, and the vertical axis actually gives you the area. Now, what we could do is we could actually take our area function and evaluate it at 500 thirds, like so. And if you take the area function and evaluate it at 500 thirds, you're going to get 83,333 1/3 square feet, right? That very much agrees with my picture here, right? Because the scale I currently have on the graph right here, these little tick marks right in here are all by 5,000s. And so notice this is somewhere between 80,000 and 85,000 square feet on the graph. So this certainly gives us a really good, clear indication that the critical number we found does actually yield a maximum area. Okay, so I think that the graph is a really nice thing to kind of spend a little bit of time with. Okay, so we have solved the problem. Now we do need to go back and answer the question, which we needed to go back and talk about. It says, what dimensions can I fence to enclose a maximum area? So I don't have the dimensions yet. I just have one dimension, which is the 500 over 3 right here. Now remember, we do know that that 3x plus y is equal to 1,000. And so you get that 3 times x, which we got to be 500 thirds, plus y is equal to 1,000. The 3's divide out, and so you get that y is equal to 500. And so our y, our long dimension here for this rectangle is 500 feet. And those are my dimensions, right? You'd want to draw this out for somebody if you were actually going to direct them to how to fence this area in. But those would be our dimensions. So drawing the picture is a nice thing to do because you can really say, okay, these are the dimensions for the picture that we're talking about in this problem right here. All right, now that took us a long time to get through that one problem, but remember, we're kind of going through everything very, very detailed as we walk through this. And I think it's a good idea for you as we encounter a problem is to stop the video and see if you can solve the problem first before I actually solve it. I think that would be a very good thing for you to do if you're watching this. All right, so we've got a good problem laid out, so now let's go on to another problem. All right, so this is a completely different kind of problem. It is geometric in nature, as a lot of them are going to be. But in this case, purely algebraic, in that what we have is we have a line, and we have a line or a linear equation, y equals 6 minus x over 2. 6 minus x over 2, okay? Or if you wanted to write that in slope-intercept form, you could write that as negative 1/2 x plus 3. Right? Those are the exact same equation. All right, so that particular equation has a x-intercept at 6, 0 right here, and it has a y-intercept at 0, 3 right here. All right, so let's say we're given this line, and that line has the equation y equals 6 minus x over 2, or negative 1/2 x plus 3, either way you want to write it. All right, what I want to do is I want to enclose a rectangle inside the triangle that has been formed, right, by the x and y axis and the line. All right, so what we're going to do is we're going to inscribe a rectangle inside the triangle formed by the line and the coordinate axes. Okay, so that rectangle is going to look something maybe possibly like this. You know, it could be a rectangle that I've just drawn right here. Put that one in pink like that. Now, it could be, it's all sorts of shapes, isn't it? So you could have a rectangle that's inscribed like this. It's a flatter rectangle. Or you could have a rectangle that's a taller one, like this one. Right? All these rectangles fit the bill that they're all inscribed inside that triangle right there. So what we want to do is we want to find the rectangle with the largest area. Okay, that's what we're after in the problem. So let me redraw this, and then we're going to walk through the steps that we've been talking about for solving this kind of problem. All right, so 1, 2, 3, 4, 5. So we have an intercept here at 6 and another one here at 3. Here is our picture. This is the equation, y equals 6 minus x over 2, or negative 1/2 x plus 3, like so. And we've got a rectangle inside that kind of looks like this. Okay. Let me kind of clean up the way that looks a little bit. So it looks a little bit cleaner. So you have negative 1/2 x plus 3 right there. Okay. Now that rectangle, if you think about it, is determined by whatever this point is right here. This point has coordinates we'll call x, y. And if that point has coordinates x, y, then this length right here is x, and this length right here is y. Okay, so now if we walk through the steps that we've been talking about for these kinds of problems, step one is to identify the quantity that you're trying to maximize or minimize. What are we trying to do? We're trying to maximize the area. Maximize has an E at the end there. Maximize the area of the rectangle. All right, and write an equation for that quantity. We're going to call that quantity A. Well, from the picture, that would just be x times y. So pretty simple equation, just like the last problem. And so now what we need is an equation that connects x and y, because this is now a function of two variables. We need it to be a function of one variable, right? And so a is a function of two variables. We want it to be a function of one variable. So we need a secondary equation. But what do we see about that point? That point, xy, lies on the line. And the line y equals -1/2 x plus 3. And so we know that y is equal to -1/2 x plus 3. Oh, whoops, and I got ahead of myself there. So the secondary equation, that equation allows us to take our function a equals xy and write it as a equals x times -1/2 x plus 3. And sure enough, we have an equation or a function of just one variable. So it's -1/2 x squared plus 3x. All right, now restrictions, the fourth step. What's the effective domain for this function? Because again, that function is a quadratic function. It's a polynomial. It's defined everywhere. So its algebraic domain is all reals. But from a practical standpoint, because of the picture I have here, right, and the fact that this intercepts here at 6, 0, the restriction on x is that x has to be greater than 0. Also, x has to be less than 6. And so x has got to be in this interval from 0 to 6. Right, x is bigger than 0, it's less than 6. It's got to be in that interval somewhere. And it's an open interval. X couldn't be 0 because you couldn't get a rectangle. X could not be 6 because you could not get a rectangle in that case. All right, so that's our fourth step. The fifth step is to find the derivative. So the derivative of this function is going to be, when you take the derivative, you're going to get -x, very simple derivative, -x plus 3 is our derivative. That's a prime. And so the critical number, right, where a prime is equal to 0 would be -x plus 3 equals 0, or x is equal to 3. So we have a nice critical number there at 3. Step 6. Does x equals 3 yield a max? Right? That's what we're hoping for. And notice in this case, the easiest way to verify that x equals 3 yields a max is simply to look at the second derivative of this function. The second derivative of this function is simply -1. And using the second derivative test, right? So I'm going to flip the screen here. So using the second derivative test, this is certainly the easiest way to do this problem. What do we have here? We have that a prime at 3 is equal to 0. And we also have that a double prime at 3 is equal to -1. It's a negative number because the second derivative is a constant. It's always -1. And so what does this prove? It proves that the function's concave down. And so, right, this is concave down. It's got to be because the second derivative is negative. We know that a prime of 3 is 0, so we know there's a horizontal tangent line there. And so what do you have to have? X equals 3 must yield a max. You could use the first derivative test. You could look at the graph, and all of those would lead you to the same conclusion. All right, so that's step 6. Now step 7 is to go ahead and answer the question, but the question is find the rectangle with the largest area. So we're looking for dimensions here again, right? Or we're looking for the point, and so we need to find the y value here, right? We know that y is equal to -1/2 x plus 3. And so when x is 3, you get y equals -1/2 times 3 plus 3, or -3/2 plus 3, or 3/2. And so what point yields that maximum area in this problem? 1, 2, 3, 4. Once again, here's my picture, right? And we're saying that the point when x is 3 and y is 3/2 yields that maximum area. And so that's this point right here. And this is the maximum area, this rectangle right here. X is 3, y is 3/2. That no other rectangle that we can inscribe inside that triangle would have an area as big as this one right here. All right, so we have now finished that problem. All right, so we're going to continue talking about some geometric problems. And let's see, okay, so I'm going to go ahead and start the next problem on a clean page right here. Let's say we have a piece of tin. Let's not necessarily say it's a piece of tin, but a piece of sheet metal. And the piece of sheet metal is 24 inches by 24 inches. All right. What we want to do is we want to cut corners of equal size so that we can maximize the volume of the box that's formed when folding the flaps that are left from the resulting piece of metal. All right, now don't panic. It's really not too big a deal geometrically, but let's look at this geometrically here real quick. So here you have a piece of sheet metal right here. It's a square piece of sheet metal. It's 24 inches by 24 inches. That's what we're told. And what we are going to do is we're going to cut out corners here of equal size, like so. And when we do that, notice that the piece of tin that we have left after we cut those corners is going to look like this. You're going to have a piece of metal that has sides like this. And like this. I'm going to try to make it relatively accurate. And this is the piece of metal that you have left. And so what are we going to do? We have flaps on that piece. If we fold along the dotted lines right here and fold those flaps up, then what are we going to do? We're going to form a box, right? And that box maybe will have a shape sort of like this. Right, with the flaps folded up. Now the box will not have a top, right? No top on this box. Now, this is actually a problem, believe it or not. I had a student once that just recently, in fact, in the last semester or two, came by and said that this is exactly a kind of problem that he encountered at the place he works, because the place he works was an air conditioning company, and they were creating drain boxes for water heaters that are sitting in people's attics. And this is exactly what they would do is, first of all, the box would not have a top to it, but they wanted some kind of a fairly shallow pan that would fit underneath a water heater, and those pans would collect any water that leaked out of the water heater, and you could drain it out. And so they were actually taking square sheets of sheet metal and punching out corners and folding up the flaps and then welding along those seams and creating a box. So this is exactly what they were doing. So what we want to do in this case is we want to go through this exact situation and try to form the box that holds the biggest volume in this problem. That's what we're trying to do, is maximize the volume. So that's number one here, is to maximize the volume. Now, if you are watching this, what I would like you to do at this point is I'd like you to stop the video and go ahead and see if you can write out an equation here for the volume, and see if you can write it as a function of one variable, and then see if you can actually solve this problem. And then come back and watch what I did and compare the two and see how you did. So that's what I would do at this point, is I would definitely stop the video. See what you can do. All right, we're back. The trick to this problem is to let the little squares, since these are squares of equal size here, let those all have dimensions x by x. All right, so if you do that, then notice that the box that you've got, here's the box, here's the base of the box I'm putting in green, that the dimensions of that base, right, and that base, by the way, would be this base down here, right, that's this base down here on our box down here. The dimensions of that base, remember that this distance was 24, but what are you doing? You're taking off x on this end and x on this end right here. And so when you take off x on each end like that, you're taking off two x's, and so this is 24 minus 2x. And this base, this dimension would have, obviously, since it's a square, would have the exact same dimensions, 24 minus 2x. And then the flaps themselves, since these distances are x, those would be the heights, when you fold them up, the heights of our box. So step 2 here would be that the volume is equal to, and this is step 2 right here, the volume would be the two bases, the two dimensions of the base multiplied together times the height. And so you've got the volume to be x times 24 minus 2x times 24 minus 2x, like so. Right, there's your volume. All right, it certainly doesn't matter what order you write those factors in. Now notice that this is already a function of one variable. And so we can skip step 3, because step 3 is to look for a secondary equation, but we kind of sidestepped the secondary equation the way we drew the picture out. And so we're ready to go on to step 4. And step 4 would be to look at the restrictions on this function. And so now if you think about this for a second, notice that the sides of the box, the sides of this sheet metal were 24 inches by 24 inches. And then if you look at those squares, notice that there's no way that x could be equal to 12, because if x was 12, those squares on each corner would be 12 by 12, and you'd be cutting out the entire piece of sheet metal. So x must be less than 12. X has to be greater than 0. So this is an open interval problem. X is greater than 0 and less than 12. Those are my restrictions here. All right, now you're going to go on and find critical numbers here. And so if it depends on how you do this problem, but if you want, you can take the derivative in this form, in the factored form, or you can go ahead and multiply everything out if you want to. I personally would just leave it in factored form for step 5 to find the critical numbers. So when I say leave it in factored form, I'm saying let's write this as v equals 24 minus 2x quantity squared, like this. And I'm going to find the derivative in that form. And so to find the derivative in that form, it's a product rule problem. So you'd have first times the derivative of the second, which is the chain rule. Here's the derivative of the outside using the power rule. And then the derivative of the inside would be -2. And that'd be plus the second times the derivative of the first, but the derivative of the first is just 1. So this is just 24 minus 2x squared, like that. So it turns out relatively nice if you do it that way. And so let's see, our v prime here would be -4x times 24 minus 2x plus 24 minus 2x squared. And so if you factor that, let me make that a little bit neater. So v prime would be equal to, take out a 24 minus 2x, and you are left in the first term with -4x, and in the second term you're left with 24 minus 2x. All right, and so v prime, if you combine like terms in that second factor, then v prime would be equal to 24 minus 2x times 24 minus 6x. Both of those have a GCF, and I'm just going to continue to factor here. So I can take out a 2 out of the first one. You get 12 minus x. And you take out a 6 out of the second one, and you're left with 4 minus x. And so v prime would be equal to 12 times 12 minus x times 4 minus x. Okay? And so the critical numbers in this case, where v prime is equal to 0, would be when x is 12 and when x is 4. But remember what the restrictions are. The restrictions in this problem were that x had to be between 0 and 12 in that open interval. And so notice that our first critical number, x equals 12, we would throw out. Couldn't be a possible solution to the problem because it's not in the restriction that we're looking at. So the critical number we're interested in is x equals 4. All right, so does x equal 4? This is step 6. Let's verify that x equals 4 actually yields a maximum volume. And again, several ways you could do this, right? You could use the first derivative test. You could use the second derivative test. You could look at the graph. So now this, if I use, and a lot of times I'll use the second derivative test just because I think it's a little bit easier to do. Sometimes I'll look at the graph also. But the second derivative in this problem, if you go ahead and take the derivative of the derivative, that 12 I'll just leave out there by sitting by itself. So you have the first factor, 12 minus x, times the derivative of the second factor, which is -1, plus the second factor times the derivative of the first. The derivative of the first is -1, and this is times 4 minus x. Like that. And so our second derivative is going to be 12 times -12 plus x minus 4 plus x. All right, and so our second derivative is going to be 12 times -16 plus 2x, like that. Or you could multiply this out if you wanted to, and second derivative would be 24x minus 192. All right, and so then what do? We evaluate our second derivative at the critical number we got where the derivative was 0. in the previous step. So we're looking at the second derivative evaluated at 4, and we get 24 times 4 minus 192, or 96 minus 192, or negative 96, which is less than 0. So what do we have here? We have that v prime of 4, the derivative at 4 is 0, but the second derivative at 4 is negative 96, which is less than 0. And the second derivative test definitely says then that there must be a maximum v value at x equals 4, like that. All right, and now if we were going to go back and answer the question, I think the question is basically what size corners are we cutting out there, right? And so what are we going to do? We're going to cut out 4 by 4 corners because x is 4. Cut out 4 by 4 corners. All right, and then the box that we get will yield the maximum volume. So if you actually calculate that in this problem and calculate the maximum volume, remember that the volume equation was x times 24 minus 2x quantity squared. So the volume at 4 would be 4 times 24 minus 8 squared. So that'd be volume would be 4 times 24 minus 8 is 16. 16 squared is 256. Like that. And so you get 1,024. So that would be our volume, is 1,024 cubic. And I think we were doing inches here, so this would be cubic inches. Like that. That would be our maximum volume. Once again, probably not a bad problem to look at the graph and see how the graph is working out in this particular problem. So because that does not take us too long to do. So let's go ahead and get rid of this function here. And the function that we've got is x times 24 minus 2x. And then that quantity is squared. All right? So this, and you obviously have to look at this in the correct interval. Remember that our effective domain was at 12, and so this is a nice picture to look at for the effective domain. So let's go ahead and take a quick picture of this problem, and let's go ahead and move this back to our whiteboard here. And make it a little bit smaller maybe. Go ahead and paste it on in. There we go. All right, so notice what we have here is that we have a maximum. First of all, notice that this function stays above the x-axis, but it has this intercept right here at 12. Right, remember that was one of our critical numbers, was at 12. Right, so notice there's no way that x could be equal to 12 in this problem physically. The other extreme value, so at 12 we notice we got a minimum there. The other extreme value here is this maximum, and notice that occurs at 4, x equals 4. And when x is 4, what are we getting? We're getting a maximum volume at 1,024. Remember, this is our x-axis, and this would be our v-axis in this problem. It would be our volume axis. Right? X represents the size of the corners, so we're saying a 4 by 4 corner, maximum volume. So this says 4 by 4 corner. Like there. And then this is our maximum volume right here. So I do think it's not a bad idea to look at these graphs and see how the graph relates to the function that you're talking about and how it fits in with the physical application that you're dealing with. All right, so we are doing really well here. The next problem I want to look at, let's look at another inscribing problem where you're inscribing a figure inside of something else. So let's say that we have this problem where we have this graph, and this is the upper half of a circle with a radius of 4. So here's the upper half of the circle. Radius of the circle is 4. That's at 4. That's at -4 right there. The equation for this circle is y equals the square root of 16 minus x squared. All right, that represents the equation for that circle, or that semicircle. So what we want to do here is we want to take a rectangle and inscribe it inside this semicircle. We've already done an inscribing problem. This one does have some differences with the first one. So we want to inscribe a rectangle that has maximum area. So inscribe a rectangle that has maximum area. All right, and so, you know, we can go to school certainly with the problem we talked about earlier, in that what we would do is we would label this point x and y, and that point, as it moves along that circle, would have to, it would determine a different rectangle wherever you move that point as you slid it around that circle. And some of those rectangles are, you know, tall and skinny. Some of them are really flat and very low down like that, very narrow. And we're looking for the one that has the maximum area. All right. Now, if you look at the picture, notice that this distance right here is x. And so if you're talking about just pure distance right here, then this distance would have to be x also. Right? Now, I know you're on the negative side. I'm just talking about distance now, the length. And so x is positive the way I've drawn the picture. And so certainly this dimension for this rectangle would have to be 2x right here. And then the height of the rectangle, this dimension, would be y, be given by the y value, right? Because this would be y right here. All right, so this is another place where I would want you to stop the video, see if you can work the problem, see if you can find the rectangle that has the maximum area that you can inscribe in there. Okay, so we're back. All right, let's see how you did. Now this problem is, there's a place in this problem that you can make a simplifying step that makes your life a lot easier. And, you know, to be fair, I had not shown you this trick yet, so if you didn't come up with this, you might have had a harder time with this problem. So step 1, what are we trying to do? We're trying to maximize area. All right, step 2, we write down an equation that gives us the area of this rectangle. So the area of this rectangle, notice, is going to be 2x times y. All right, it's involving too many variables, so we need a secondary equation for step 3. So our secondary equation, we do know that that point xy has to be on that semicircle. So the secondary equation in this problem is y equals the square root of 16 minus x squared, right? That xy has to be on that semicircle, so it must satisfy that equation. And so our area equation becomes 2x times the square root of 16 minus x squared. So let me clean that up a little bit, the way it looks. Okay, try that again. So 2x times the square root of 16 minus x squared. All right. Now, step 4 are restrictions. And the restrictions in this case would be that x has to be between 0 and 4. X could not be equal to 0, x could not be equal to 4. So x has to be somewhere between 0 and 4. All right, and so the next thing we would do here is we would find our critical numbers, and this is where you make a simplifying procedure. is because what are we going to have to do? We're going to have to find a prime, but a, oh my gosh, has a radical in it. It's a product rule. So you've got this chain rule inside the product rule. A prime is yucky. A prime is yucky here, right? We don't really like that finding the derivative is going to be as messy as it is. So what we do here is notice if we squared both sides of this equation and got a squared equals 4x squared times, and notice if I square both sides, the radical goes away, and I get 16 minus x squared right there. So notice that a squared is just a polynomial. Right? A squared is just 64x squared minus 4x to the 4th power. Well, the deal is that wherever A has a max, A squared must have a max also. So in other words, maximizing A squared would yield the same answer as if I maximized A. Much easier to take the derivative of A squared. And so that is what I'm going to do. Is I'm going to take the derivative of this function right here. And so I'm going to go ahead and copy that, paste it to the next page. Whoops. Go ahead and paste it to the next page. Like that. And I'm going to find the critical numbers for this function, and I'm going to maximize A squared instead. So maximize A squared instead. Much easier to do that. And so that simplifying procedure where I square both sides frequently works. So it's this step right here. That works a lot of times when you have a multiplication problem where you have square roots in it like that. And just squaring both sides just makes your life so much easier as far as calculating the derivative. So definitely worth taking that little detour right there. Can make this problem much easier. All right, so now we're on to A squared prime. Right, we're finding the critical numbers now. So A squared prime would be 128x minus 16x cubed. All right, and then we can factor that. A squared prime I could take out as 16x, and I do that, I'm left with 8 minus x squared. Okay. And so A squared prime is equal to 0 when x is 0. Right? I throw that one out. And when x squared is equal to 8, which means when x is equal to, and remember, by the way I drew the picture, x had to be positive, and so this would be the square root of 8, which would be 2 times the square root of 2. So 2 times the square root of 2 is probably the value that we're after. So what we want to do now, right, for step 6, right, that was step 5 right there. Step 6 is to go ahead and verify this yields a maximum. Verify that x equals square root of 8, which is 2 square root of 2, yields a maximum area. And we could certainly use the second derivative test here if we wanted to. The second derivative, A squared double prime, is equal to 128 minus 48 x squared, like so. And so now remember what we would do is we would take our second derivative and we would evaluate it at the square root of 8, or 2 square root of 2. And so that'd be 128 minus 48 times x squared, and x squared would be 8 in this case. And so you get 128 minus 320, 64, 384, like so. We don't even care what that number is. We just know that that is got to be less than 0. Right? And that's all that we need. So what do we know? That A squared prime of 2 square root of 2, or the square root of 8, is equal to 0, then a squared double prime evaluated at 2 square root of 2 is negative. And so that means the function's got to be concave down at that spot, means that 2 square root of 2, x equals 2 square root of 2 yields a maximum area. Now, in solving this problem, if you were going to do this graphically, what I would do is I would graph. So graphically, I would graph the original function. A equals, and the original function, remember, that we set up for area was 2x times the square root of 16 minus x squared. 2x times the square root of 16 minus x squared. And what you want to do is verify that at 2 square root of 2, which is approximately 2.8, that you're actually getting a maximum area at that spot. So that would be a good problem to look at graphically. So let's go ahead and take care of that real quick. Okay, so our function is going to be 2x times the square root of 16 minus x squared. Close the parentheses there. And when I look at the graph here, definitely need to kind of expand this out. Remember, what we saw was that this is the piece we're interested in, the piece between 0 and 4. And we saw that this graph is yielding a maximum right at about 2.8. And sure enough, if you look at our graph there, and again, probably should take a picture of this. Bring it back to my notebook here. Go to the next page. Bring up that picture. And what do we have here? That at 2.8, what do we get? We get a maximum for the function right there. And then this value right here, which looks to be at about 16, somewhere about 16 would be our maximum area. Remember, this would be our area axis, and this would be our x-axis, and x represents the x-coordinate of that point on the graph there. Right, going back all the way back to this problem, right? The x is that x value right there. All right, so we have solved that problem, and we verified it a couple of different ways as far as the how to find the maximum there. All right, so the next problem. So what we're going to do is we're going to finish this with a problem that's really, really different. So let's say, and so this is our setup for the problem. Last problem for this lecture is, let's say that we have a shoreline right here. Okay, and you're sitting right here at about 2 miles off the shore. This is an exaggeration, a complete exaggeration, by the way. And you need to get onshore. So this is land, this is water right here. This is land right here. Right, and you need to get to this point, which is 1 mile inland right here, and you need to get there as fast as you can. And let's say that you can swim at 2 miles per hour, and you can run at 4 miles per hour. And what we want to do is we want to minimize the length of time it takes to get from point A to point B. Now, the reason why this is kind of a difficult question to solve is because there's lots of different paths that the person could take. Oh yeah, and one other piece of information I kind of left out here is that these points here are exactly 3 miles apart on the shoreline right here. That's 3 miles right there. See, so what could happen here is the optimal solution could possibly be that you swim straight to the shoreline and then head to B and run that way, like that. That's a possible solution to the problem. Now, there could be a better solution. A better solution possibly would be to swim somewhere to a point somewhere in between and then run. Now, notice that that's a shorter distance right there in blue. So the question is, does the fact that you swim slower than you can run, does that affect, that spot, or would it mean that you should just swim straight to shore? And then finally, there could be even a third solution. The third solution, though not likely in this problem, certainly would be you could swim straight to that point right there and then head to point B that way. So notice that there's, and then it could be anything in between, right? So basically, we could frame the problem this way, is that how far downstream or down the shoreline do you swim to so that you can get from point A to point B in the minimum amount of time, right? That's really what you're talking about doing here. Now, and so what could be true here? That if you swim straight to the shore, then x would be 0. And if you swim to this point over here, x would be equal to 3. So notice in this case, the restriction on x, we'll just go ahead and write that down right away. The restriction on x is that x has to be in the closed interval from 0 to 3. This is a closed interval problem, and x could be anything from 0 to x equals 3 or something in between. All right, so now what are you trying to do here? You're trying to minimize time. So we minimize time, and we'll call that t. And if you think about it, if we let the time for the first part of the trip be t1, so that's the time in water. So time in water is t1. And time 2 is time on land. Then t here in this problem is actually t1 plus t2. Right? Time on the water, time in the water, plus time on land. Right? And so what we're trying to do is we're trying to kind of come up with an equation. We need to kind of create equations that involve x here. Now, one thing I will also point out to you is that, remember, that rate times time is equal to distance. So time, which is what we're interested in this problem, is distance divided by rate. And so what we need are the distances for these two triangles, basically, is what you're talking about. So I'm going to redraw this picture and kind of eliminate all that extra stuff on there and just look at the triangles here. Here's point A right here. I know that that side is length 2. Here's point B over here. I know that side is length is 1. And I know, let's see, if I'm going to draw a triangle like this and then over this way, that this distance is x. And because the total distance is 3, then this would have to be 3 minus x right here. And so notice we do have the distance formula here, or the Pythagorean theorem, and you can use the Pythagorean theorem to write these distances. And so this distance right here, using the Pythagorean theorem, would have to be the square root of x squared plus 4. That would have to be the distance there. And the distance for the for this side right here, well, let's see, if you're going to have trouble with this, let me write it out. This is 3 minus x squared. Let's say that this distance right here is distance 2. So 3 minus x squared plus 1 squared would have to be equal to distance 2 squared. Right? And so distance 2 would be the square root of that expression. So that would be 9 minus 6x plus x squared plus 1. So distance 2 would be equal to the square root of x squared minus 6x plus 10. Okay, so what would, so those are my, that's my distance, and square root of x squared plus 4 would be distance 1. So what would time 1 be in this problem? Time 1 would be distance 1, square root of x squared plus 4, divided by the rate that you can swim, which is 2. And time 2 would be distance 2, which is the square root of x squared minus 6x plus 10, divided by the rate you could run on land, which would be 4. And so those would be my 2 times right there. And so remember what t is. T is t1 plus t2 in this problem. So going to the next page here, right, we know that t is equal to t1 plus t2. We know that time would be equal to the square root of x squared plus 4 over 2 plus the square root of x squared minus 6x plus 10 over 4. We also know that x has to have this restriction, that x must be in the interval from 0 to 3, right? That x has to be inside that interval. All right, now this is a problem where you cannot square both sides because there's addition. Because there is addition, you cannot square both sides of the equation. In other words, you're stuck with this form right here, and this is how you have to calculate the derivative. So, well, okay, that'll be interesting. So t prime, well, first of all, before we say t prime, let's rewrite t a little bit. That this is 1/2 times x squared plus 4 to the 1/2 plus 1/4 times x squared minus 6x plus 10 to the 1/2, like so. So now t prime would be equal to, chain rule in both cases, this would be 1/4 times x squared plus 4 to the negative 1/2 times 2x. That's derivative of the outside times the derivative of the inside. Plus 1/8 times x squared minus 6x plus 10 to the negative 1/2 times 2x minus 6. Okay, so t prime would be 2x over 4 times the square root of x squared plus 4 plus 2x minus 6 over 8 times the square root of x squared minus 6x plus 10. Yuck. Now, you could cancel out a 2 in that first fraction and reduce it, and you have x over 2 times the square root of x squared plus 4. And in the second fraction, you could also divide out a 2, which would leave you with x minus 3 over 4 times the square root of x squared minus 6x plus 10. Like so. All right, so now what do? You know, we got a tough road ahead of us on this problem. We set t prime equal to 0, so we set this expression, which just looks horrible, equal to 0, and we got to solve this equation. And I wanted to work a problem where this was tough to go through, so you could see how this kind of operates. So what I would do here is I would go ahead, for example, and subtract that first fraction. You know, so you have negative x over 2 times the square root of x squared plus 4 like this. And then you could actually cross multiply, believe it or not, here, because it's just a fraction equals a fraction. And so you could cross multiply to see how this is going to work out. So you've got negative 4x times the square root of x squared minus 6x plus 10 equals 2 times x minus 3 times the square root of x squared plus 4. Oh my gosh, like that. All right, and then what I would do at that point is I definitely need to, probably wouldn't remember that on the next page, so I'm going to copy that and bring it over to the next page. And let's see if we can actually solve this equation. Oh my gosh. Right, how are we going to do that? Well, if we square both sides of the equation, we can get rid of the radicals. So luckily, squaring both sides is not too horrible. So square both sides, and you get 16x squared times x squared minus 6x plus 10 equals 4 times x minus 3 squared, which is x squared minus 6x plus 9, times x squared plus 4. Like that. Wow. Right? Now I can divide out of 4, which only does a minimal amount of good here, but at least it does something. So divide out of 4 there, gets rid of the constant on the right side at least. And now you have to solve this equation for x, right? And so you multiply all this out, collect like terms. Let's see what we can do here. So if you have 4x to the 4th minus 24x squared minus 24x squared plus 40x squared. I'm sorry, 40. Try that again. So 4x to the 4th minus 24x cubed, that's better, plus 40x squared is equal to, and on the other side of the equation, this would be x to the 4th minus 6x cubed plus 9x squared plus 4x squared minus 24x plus 36. If you multiply all that out. So you have 4x to the 4th minus 24x cubed plus 40x squared equals x to the 4th minus 6x cubed plus 13x squared minus 24x plus 36. And now you get everything over on one side of the equation. So you subtract x to the 4th, and that gives me 3x to the 4th. And then you add 6x cubed. So I add 6x cubed, and I get minus 18x cubed. And I subtract 13x squared, and so I have 27x squared. And then I add 24x and subtract 36. And then you get that 4th degree polynomial. Now you could divide it out of 3 there, which at least makes it x to the 4th minus 6x cubed plus 9x squared plus 8x minus 12 equals 0, like that. And what I would do at this point is I would go ahead, you could solve that like a college algebra student would solve a polynomial equation. So you could go through and use synthetic division and all that. What I'm going to do, though, is I'm just going to go to this graphically. Go to this graphically, and let's have a look at that function graphically and see what's happening here, right? Because we want to kind of get to the heart of the problem here at the end. So remember, we're trying to see how far down shore we would swim. Probably have forgotten what we're even solving right now because the problem has been quite lengthy. Minus 12. So let's see. So you have x to the 4th minus 6x cubed plus 9x squared plus 8x minus 12. And so if I graph that equation, notice that very quickly I come up with the fact that 1 must be a solution to that equation. And so that's what I needed right there. And so I'm just going to use the graph, and I'm going to say from the graph, x equals 1 is a solution. And that's the only one, that's the one we are looking for. Remember, it had to be in the interval from 0 to 3 anyway. And so I've got x equals 1. And then you'd have to actually verify, step 6 is verify this yields a max. And I would look at the graph again for this problem. So I would look at the graph now, but now remember what you're maximizing. So I'm maximizing our function t, and remember our function t is this function, the square root of x squared plus 4 over 2 plus the square root of x squared minus 6x plus 10 over 4. Right, so that's the graph that you're looking at. Be careful what you're actually maximizing or minimizing. In this case, oh, and one thing I said yields a max, but remember, what are we trying to do? We're trying to yield a minimum here. All right, so I would actually look at the graph at this point, and especially with something that's this complicated. And so let's see. So I've got the square root of x squared plus 4. So square root of x squared plus 4, close the parentheses, divide that by 2, and then add the square root of x squared minus 6x plus 10, squared minus 6x plus 10. Please be careful how you're entering this. And I'm going to divide that by 4. Right? And so when I do that and I graph this, remember, we're graphing this between, got to really kind of stretch this out a little bit. We're graphing it between 0 and 4 right here. So this is a really, really good problem to look at as far as absolute maxes and mins. So I definitely want to take a picture of this and bring it back into my whiteboard here so we can talk about that, and then we'll be finished with the day. All right, so I want to take that last screenshot right there, and I think I just want to leave it big like that. All right, so now remember that the interval was from 0 to 3. So if you're looking at the interval here on the x-axis, right, x had to be between 0 and 3. And so now remember, this is our x-axis right here. And so that axis tells us, remember what x represents. I mean, this has been a while since we've done this at the beginning of the problem. But remember, x represents how far downstream you're swimming, or down the shoreline you're swimming to get to the land, right? That's what x represented in this picture. So it's been a long time since we talked about that. And then our vertical axis is actually our t-axis. Right, this is the t-axis right here. That's our time axis. And if we're trying to minimize the time, we're looking at this piece of the graph right here, right, from 0 to 3. This piece right here is what we're interested in. And what do we see? That when x is equal to 1, we get a minimum time. Sure enough, right, somewhere between 1 and 2 hours. And notice that, so x equals 1 yields a minimum time. And then what about x equals 3? X equals 3 is an endpoint, and x equals 3 yields a maximum time. A little bit more than 2 hours. Right, and you know, remember what that makes sense, because if you think about the physical aspects of the problem, remember x equals 3 is if you swam all the way to the point on the shore opposite point B. Right, that was x equals 3, and we were pretty clear. It looked pretty clear from the application here that that would be the maximum length of time. But what we're saying is if you swim 1 mile downshore, this would yield a minimum length of time. So that's x equals 1, which is right here. And that would yield a minimum length of time. Okay, so this is a very lengthy problem, but I wanted you to see a hard problem and how it's worked out. So we've worked through several different examples here, definitely. I'm going to be sending you emails with some practice problems, some basic practice problems for you to look at. Optimization problems are notoriously difficult for students, and so I want you to get started on this, and I'm going to be kind of harassing you on email to get going on practicing max, min, and optimization problems as we head into the third exam, okay? So you guys have a great day. You'll definitely be hearing from me over the next day or two about max min problems by email, and be looking for your homework 3 grade being posted in the next couple days and your exam 2 grade being posted middle of next week. Have a great day. Thank you.